Today we're gonna start talking about the chapter 6. So chapter 6 is about the how we're gonna learn about the several types of organic reactions. And then when you think about this one, there are four types of reaction we can think of. The first one is addition reaction. So one example I can give you is whenever you have alkene. So alkene simply means there's a compound that has a double bond on it. So let's say we have a double bond between these two carbons and over here. And we can try to apply some other compounds out here. And then they might give you new products, which looks like this. So we call this addition reaction because we simply added a new component on the starting material, your reactants over here. So you have this hydrogen and bromine added on your compound. So we call this addition reaction. Okay. Make sense, right? Make good, right? And then the second one. Second one we call this, second type of organic reaction is what we call elimination. Okay. So also I can give you some example here. So if you have any compound that has OH groups, this is what we call hydroxy groups here, OH group, hydroxy group here. So if that compound that has a hydroxy group, we normally call this alcohol. You guys know. So this is alcohol. And then if we have some neighboring hydrogen over here, whenever you do use acid catalyst, and then some acidic compounds comes in, kind of behave like a catalyst for these reactions. And then if you think about these two, we'll be actually leave this compound in form of H2. Okay. So you see, once they have a hydroxy group and a hydrogen on these two carbons, but in the elimination reaction with this acid catalyst, which is any acid that can behave like a catalyst, you can have some compounds without those two, which will be in form of water here. So this is eliminated from this compound. So we call this elimination. Oh. This is what we call elimination reaction over here. So this is the what we call actually dehydration. So you actually remove the water from the compound. So dehydration is kind of a type of elimination reaction. So this is one example. Okay. Makes sense, right? Okay. All right. So do you copy, right? Copy. The third type is the what we call substitution reaction. So if you have compounds, okay, and then we're gonna interact this compounds with water, okay, with water. And then what happens to this one is they're going to have a carboxylic group over here. So I want you to look at this part here and here. And then you're going to have methanol over So what happens to this one is if you look at this one, this is coming from here, okay, and this is it over here. Okay, so it's simply water comes in, and this is substitution reactions. It replaces these groups over here to the hydroxy group over here. So in here, it makes carboxylic groups on here instead of the ester. Okay? So we substitute these groups to water, like just the hydrogen goes to the other the pre-existing groups. We're taking the hydrogen here to become ethanol, and they become carboxylic groups over here. This is why we call this reaction substitution reactions. So it kind of substitute over here. And by now, you guys wonder how did it happen, right? Like even number 1, 2, 3. We're gonna do this in detail later chapters. Okay? Don't worry about it. But for now, I just want you to remember what type of reaction we have. So we're gonna how we're gonna recognize or classify those type of reactions. Okay, let's go number 4, and I will explain more. Number 4. Is what we call the rearrangement. Okay. So, for example, if you have if we have this type of compounds over here, okay, and then you're going to, this is actually one part of the glycolysis. You're just taking bio class. You are? Oh. So this is one step you can do. So once you have a dihydroxy ester phosphate over here, in a step of the glycolysis, you're gonna have these two will be switching each other. So you're gonna have so this one will have a hydroxy group over here now, and this is the aldehyde groups over here. So this is the aldehyde 3 phosphate over here. So this is the obviously good example of rearrangement. We just rearrange those two groups on different carbons now in different position and here over there. Okay. So this is the four types of the organic reaction. So this is simply just rearranging the groups on the carbons and one to another. Okay. So makes sense, right? Okay. So once again, we just learned what are those the good example of those 4 types of the organic reactions. We're gonna learn sometimes for certain specific organic chemical reactions. We're gonna learn how it really happen in detail. We call them mechanism. So mechanism simply means we're gonna explain how did that certain type of organic reaction happen in very detail by showing the movements of electrons on the molecules. So we're gonna show you how the electrons are moved in the bondings, well, how they make a new bonding from getting a pair of electron from other elements and so forth. And all detailed information, we all call this a mechanism. So this is what we're gonna do for at least several very good examples of the organic reactions in any chapters from chapter 6. Okay? So we call this mechanism over here. So before we get to the mechanism, there's one more thing I want you to no, is we have mainly two reactions by doing with the mechanism thing-wise. Okay? So the first thing is what we call radical reaction. The other one is the polar reaction. Okay? So the radical reaction simply means you're going to have a radical compound, or radicals, you can say. Radical compounds will be involved in this type of mechanism. So you guys remember what radical means from Gen Chem 2? So radical simply means you have the molecules that have odd numbers of electrons on the available for the bonding or breakage of the bond. Okay, so this is obviously, if you think about the Pauli exclusion rule and all the atomic model we think about from Gen Chem 1 and 2, the radicals are usually very unstable. Very unstable. Okay? So this is but sometimes we're gonna have the radical reactions in the homogeneous chemical reactions. So this is one type of thing you can do in a mechanism process. The other one is polar reactions. So polar reaction simply means that you have a certain element that has more stronger power to pull the electron toward themselves. So they're going to have fully charged with a pair of electron. So if this is A and B, okay. So let's do it this way. This is better. So if you have radical reactions like here, like A and A, do you see if there are same chemical elements or the elements that have a similar electronegativity, when they break apart, they try to do in this way. Okay, so if you think about the single bond over here, this is simply the common area. You can find the pair of electron, right? So that means they have 2 electrons in there, and this one single bond over there. But when they break apart, there's no specific element can have a very dominant power to get all these 2 electrons to themselves. So what happens to this one is they try to get like equally. So I'll get 1, you get 1, because we equally strong, right? So they try to get 1 for each. So by doing this, this will have only 1 electron on each, which is obviously odd numbers of electrons they can use for the reactions. So this will become radical reactions. So this is a good step of the radical reactions you may see on the other example of radical reactions. The bipolar reaction is is the difference. So electronegativity wise, if B or A are different, so different in electronegativity. So maybe B is high in electronegativity means B will have a lot higher force or the strength to pull those 2 electrons to themselves. So A is like a loser here, and B is a winner that gets all the electrons to themselves. So what happens to this one is there's 2 electrons in here as well. The B gets all, becoming a winner, and A lose all the 2 electrons and loser. Okay. So as you can see, it's different how they arrange the electrons at the breakage of the bond is totally different from the radical reaction and the polar reactions. Polar reaction, so we call this polar reaction because it's involving some like polarity or some electronegativity factor is involved in this type of polar reactions. But the radical is simply just homocleavage of the bonding, so that gets only 1 for each. So that is major difference between these 2 reactions. You may need to know for whenever you try to explain something in mechanism. Because mechanism is indeed what? When we speak in, you need to explain how does electron move. If you don't understand these 2 it's maybe difficult to explain. Okay, makes sense, right? Okay, perfect, great. All right, that's good. All right, so let's just start with the radical rate. Okay, so the one thing I can give you is you have a methane over here, okay, and you have a chlorine, okay, diatomic molecule, right? And then eventually, if you put the enough amount of the light, apply this reaction over here, you're gonna get the products, and they are over here. So obviously, if you want to explain this one by showing some mechanism, once again, you need to show how these electrons move and the reactants and the products over here. What happened to this one is here. You could think about this one closely. This is obviously radical reaction because this will show you the same electronegativity. So when they break apart, they do this. Okay, makes sense, right? Because they don't have a difference in the electronegativity. They'll break apart in the like half and half homonucleus breakage of the bonding. So they have one electron on electron. So this is a good example of radical reaction over here. Okay? And then whenever I do this, the one thing I just want you to remember is whenever you break this one in half and half in the radical reactions, I do fishy hook, or you can call this the half-headed arrow, meaning its arrow looks like this one, right? But half-headed or fish hook looks like this. Okay, so if you do fish hook arrow like this one, you're showing the motion or the movement of the one electron at a time. So one goes on here, the other goes on here. That's why we have these two radicals. Okay, so this is what we call fish hook or the half-headed arrow. It's up to you how to call it, but just the point here is you need to do this one when you want to show the motion of one electron. Okay, so whenever you do the polar reaction over here, you're gonna do full-headed arrow, and then if you show this one, like I said, whenever I did this one, right? It's showing here, okay. And then you need to do this one, okay? So then this full-headed arrow will show you the movement of the two electrons, okay? So this is the difference between the full-headed arrow, half-headed arrow. This is something you'll see a lot in the mechanism, so please remember this. So if I do this, it means two electrons move to some space at the same time, or the half-head or the fish hook is just one electron in each. Anyway, makes sense, right? Okay. So please remember this one for whenever I start to explain the mechanism later time. We'll use more often the full-headed arrow because most of the reaction we're going to do is the polar reactions. But there are a few good examples of radical reactions we're going to do. So this is one. So we have this one over here. And then if you think about this one over here, hydrogen and carbon is not so different in electronegativity. So this is what we call this what? Non-polar covalent bond over here. In overall, it's also non-polar as well. So in this case, they can also do this brick is over here, okay? Because they're not so different in electronegativity. And then what happened to this one is this one goes to this. So the one goes to one of the electrons that are on the hydrogen, and this one goes to. So if that happens, you'll see this one, right? Okay. But they go in this way. That means they're going to make a new bond between hydrogen. Okay. And then in this case over here, you have also the possibility you can do this one. Okay, so eventually you can have a part that looks like this. And obviously, in the termination reactions, it is also possible too. They can do Cl, Cl back together. You can also saw this one, but also they can do this one as well. This is also possible. But anyway, you can mainly have those two products in this type of radical reactions. Okay, so makes sense, right? We good? Okay, perfect. Great. Okay, so there's a couple more things I want to do before we get into the polar reactions. Okay? So whenever we do the polar reaction here, there's one thing I want to talk about is polarizability. Okay. So polarizability simply means the measure of the response of atoms in a molecule to an external electronical influence. Okay? And you guys thinking what it really means, right? So I'll tell you what. So polarizability is kind of a passive term. So do you guys remember the polarity, right? Polarity means because of the gap or difference in the huge difference in the electron the electronegativity, these compounds in overall will have some degree of polarity. Means it's being polar. So it's more like an active term. The polarizability is they're being polarized by something that is the external electronical field or the interactions or influence. So if there is any external, like some other environments that makes the compounds being more like a polar, is polarizability. So that's like it's passive term. So it's not being themselves like I can be polar now. It's more like when we have some external environment, electronically different, they can change the polarity of the compounds or how they interact, how they show the response. That is polarizability. Kind of makes sense. I'll show you some example over here. So, so if you think about this one over here, the whenever you have this one over here, electronegativity wise, they're almost same. This is about 2.5. This is 2.58 or something, but means almost same. But whenever you do have whenever you do polar reactions, you're actually going to see this is a slightly negative, slightly positive anyway, even though they're not so different in electronegativity because of the polarizability. Because these two are different in how they react to the external electronical influence. Because if you look at the periodic table over there, you see the carbons in the second period and the sulfur is the third period, right? So obviously, which one is bigger? Sulfur, right? Perfect. The sulfur is much bigger than carbon over there. But the thing is, if you have a lot bigger space to store the electron inside. Whenever you have some external electronic influence that try to affect on the arrangement of the electron inside, it's obviously harder for the sulfur to maintain the position of the electrons. And they can, because those electrons on the most outer shell from the sulfur will be the most loosely held by sulfur. So they have a more chance for this one, the bigger atoms, bigger elements that has the influence by the external electronic influence a lot more than the one that is smaller. Kind of makes sense. So this the bottom line is the sulfur there, but it's bigger. They have a lot more space to control the electron, so they can't really have a much respond to the external electronic influence. So they'll get more affected by the external electronic influence than the ones of the carbon. That's why it becomes still a bit very slightly polar, up and down, negative and positive, because of their own polarizability difference. So this is a good example of polarizability. Not only for when you do the polar reaction, not only for the electronegativity, but also you need to think about the polarizability. Make sense? Kind of makes sense? We good? All right, so this is the case. Okay. Oh, so there's one more thing. I promise there's one more thing I want to do before we move on to the polar reaction. So there's one we call nucleophile. Okay. And there's another one we call electrophile. Okay. Electrophile. So nucleophile is simply they likes nucleus. And then the electrophile likes electrons. So if you think about the nucleus, what is it made of? Nucleus is made of protons and neutrons, right? Perfect. So this is the same as what? Something that is positive. So we have some compounds or some molecule that likes to chase something that is positive. We call that is nucleophile, because the file, you guys already know this, right? Means it's like something, but they like nucleus. So we call this as nucleophile. So any molecule, the compounds that chasing that something is positive to make the bond to, that is what we call the nucleophile. Okay. So the electrophile here is the totally opposite. So they try to looking for something that is negative opposite electron. They're looking for something that is more negative elements or negative charged molecules and so forth. Then if they're chasing those, we call this electrophile over here. So obviously, if you think about the Coulomb's law we learned several times in Chem 1 and 2, nucleophile will be what? Obviously, negatively charged, or neutral sometimes, but most likely nucleophile will be negatively charged. Sometimes they're neutral, but when they become negative charged, they can be more strong. They can be stronger nucleophile because they'll have more intention. They will have more tendency to chase for something that's positive when it's negative charge. So when the same here. So if that is something you have a electrophile, meaning most likely it's going to be positively charged molecular compounds. So that is why they're going to looking for something that's negative, so they can be proceeded in the polar reactions over here. Okay. So those are the two terms we're gonna talk about many times. Okay. Especially the first example that we're gonna do on Wednesday is these are the terms that we're gonna use a lot. Okay. So this is something you cannot miss in the polar reactions because of their nucleophile and electrophile, they're going to have a full motion of the two electrons at the same time. So normally, this is how we write in the chemical equation for nucleophile, and this is the electrophile. So let's say you have a negative charge. It doesn't have to be always negative charge, but let's say we have a negative charge nucleophile, and obviously most of the electrophile is positive charge, right? And then they try to show you four-headed arrow. You see the four-headed arrow over here. So they can be make the bonds like this. Okay. So in this case, you're gonna see the the one pair of electron move on the same position at the same time. Okay. So this is the something you're gonna see a lot in the polar reactions we're gonna do on Wednesday. So I'll just stop here today.